Welcome back to our webinar course. I hope you are ready for another interesting and informative session. Our second webinar organized by Zemgale Regional Energy Agency from Latvia and I guess Oslofjord from Norway. This goes under the umbrella of the project Bridging the Gap Between Research and Education for the Circular Bioeconomy, and we are going to explore circular agricultural practices that offer significantly lower footprints compared to traditional linear farming. Our webinar will be recorded as previous one, so you can share and get information later. And I am Gundars Reiders. I'll be serving as your moderator, and Inga, my co-host. Good morning, Inga. How are you?
Nice. Good morning, everyone. Thanks.
Nice. And Selma Amali, good morning to you as well. You're making a great job in putting us together for the second time.
Good morning.
Good morning. I would like to say hello to Udis, our Zoom administrator. He's behind the scenes. Hello. Yeah, we had last time we had a great 4 presentations, so I'm looking forward to today's presenters as well. After each presentation, there will be 10 minutes approximately time for your questions, so you can write your questions, remarks, comments in a chat section, chat room. Don't hesitate to do that. Yeah, it could be, I think, a very interesting session today. And let me introduce our first speaker, Tholes Allan Andrade, Aarhus University, Denmark. Good morning, Tholes. He's graduated in chemical engineering and works as a postdoc at Aarhus University, Denmark, in Green Biorefining Technologies Group. His main tasks are related to optimizing protein extraction from different green biomasses. So welcome, Tholes. You are welcome to speak.
Hi, good morning. Thank you for the invitation and also for the introduction. I will share my screen. Please let me know if everything is correct, if you can see my slides. Is it loaded? Yes, great. So yeah, my name is Thales and I'm a postdoc at Aarhus University with a chemical engineering background. Here at Aarhus University, I work at the Green Biorefining Technologies Group, where we have a demonstration scale platform where we focus on mainly on extracting green protein from different types of biomasses. Yeah, so the main challenge here in our case is due to the global increasing of the population, which leads to a higher meat production. And this production grows mainly in the pig and poultry sectors, and which leads to a high dependence on soybean importation to be used as feed for those types of animals in EU. This makes food industry very vulnerable to change in the world market. Denmark is one of the most intensive productions in agriculture and is also one of the leaders in pig breeding and pig meat production. Like the rest of the world, it faces a lot of environmental challenges also related to nitrogen leaching. Denmark has this commitment goal to reduce the greenhouse gas emissions by 70% up to 2030, and agriculture is responsible for a fourth of these total emissions. On top of that, there is a strong interest, political interest in the implementation of those green biorefineries in the country. We even have like some visits already from the Ministry of Environment and Food of Denmark in our plant. So the idea is to change from annual croppings to perennial cropping system. And this, the utilization of perennial cropping has a lot of positive impacts. For example, reducing the nitrogen leaching when you compare grasses and legumes. This leaching is lower compared to other cases. The use of pesticides is also not necessary, and have a positive soil carbon input. In this case, the perennial grasses, they are capable of absorbing the carbon dioxide. And in the green biorefinery, this carbon goes to many different kinds of applications, with a total potential sequestration of 2 to 3 tons of carbon per hectare per year. So the use of protein from green biomasses is beneficial because the protein, they are actually in the leaves itself, and we have an active growth of the biomass during the entire season, with a very attractive amino acid profile compared to other protein sources. The protein content is quite high, compared to other of those sources, as well of the main amino acids that are of interest for this feed. The concept of the green biorefinery is actually quite old. It has been investigated for many decades, and the biggest limitation is actually the commercial success, and the biggest question is how to unlock the potential of green biorefineries for emerging bioeconomy and make it into a widespread commercial success. In our base case chain, we have the biomass, the green biomass that is harvested and sent into the green biorefinery, where we will be mostly extracting the protein in the protein concentrate fraction that is mostly used for monogastric animal feed, as well as 2 other byproducts, which is the fiber that in the base case is used for ruminant animal feed, while the residual liquid brown juice that we call it here, together with the manure from those animals, is sent to a biogas plant, in which we can provide heat and power to the green biorefinery, and the digestate can be sent to the field as fertilizer. In this case, in the whole process, we can reduce nitrogen leaching, we can increase the business in local areas, as well as having a local production of feed protein and minimizing the reliance on importation. So the green biorefinery can actually fit in the whole structure of a bio scenario. So in this case, you can see green biorefinery and other sources. They can be combined together, for example, with the lignocellulosic biorefinery, in where you have the protein extracted and used for feed and food applications, as well as different types of chemicals and fuels, and also heat and energy, among other products. So our investigation here in Aarhus University started in this field back in 2015 in lab scale, progressing to pilot scale. And then in 2019 is where we had the demonstration scale platform that was established in Viborg in Denmark, with an input of a maximum of 10 tons per hour of biomass that can be processed. It's a very flexible design, which allows us to adjust the plant according to our needs, and very automatic control and extended data collection. We focus mainly in grasses, which is ryegrass and Festuloleum, as well as different types of legumes. We have white clover, red clover, and lucerne mainly. So the idea is that we have a high quality protein located close to the biorefinery, so we can start processing as fast as possible with a high productivity per hectare of those biomasses, and with a low environmental impact. So in the case here, as we start with the green biomass, where we have this pressing, where the green juice rich in the protein is separated from the press cake, the fiber press cake, and the fiber press cake undergo a process protein precipitation step. When the protein, and afterwards the protein is centrifugated and separated from the brown juice that has other applications, and the protein concentrate here is mainly used for monogastric feed. So just some numbers here. When we started with the protein, this protein goes to the initially to the wet fractionation, and in this case, the harvest biomass undergoes a maceration step. It's more like a cutting step where we can crush the biomass to a smaller particle size to enhance the separation of the fiber and the juice in the pressing stage. So the fiber, the solid fraction is the fiber press cake, while the liquid fraction is the green juice that undergoes protein precipitation. That could be by pH shift, but also chemical treatment, and the one that we use the most here at Aarhus University, which is the heat precipitation of the protein. So we basically heat at up to 85 degrees Celsius our green juice, and we have the separation of the residual juice and the protein concentrate. So many factors impact the quality and the yield of our protein. As I mentioned many times, the biomass quality, it's one of the important factors, and also starting immediately after harvesting, so we can avoid browning, and also we can avoid the degradation of the protein into amino acids. And of course, the way we process regarding to our related to our needs in the target. So I will show some examples of what have been doing and what we have investigating since 2019 mainly. So as I mentioned, many different types of grasses and legumes were investigated. And we can see that the yield of the protein concentrate increased with a higher protein, plant nitrogen content. And also legumes have a higher yield of the protein concentrate compared to grasses, and this is because of a more leafy structure compared to the stems that it is in the grass. Another optimization that we have been done is in terms of the maceration. As I mentioned, after harvesting the biomass, we have this step where we, before pressing and splitting the fiber and the green juice, we have this maceration step where we break down the biomass. We generally do this standard, more simple case. There is one stage only, but we have investigated a more severe, more intense maceration where we add additional unity operations to enhance the dry matter content and the crude protein content in our protein concentrate. So if you compare in terms of the dry matter, for example, in this yellow area here, when we have a normal maceration, 6% of the dry matter is in the protein concentrate, and we could increase to 19%. And in the same case, the protein content, out of 100% of the protein in the biomass, 17 ended up in here, in the protein concentrate in a normal case, while that we could achieve 44% in the protein concentrate of the protein, the crude protein content. So when we actually now observing the dark green zones here, so for a more severe maceration, we tend to observe a higher dry matter content if we increase these maceration steps. Of course, with the addition of additional equipment, we have a higher energy consumption. So more intense macerations lead to more energy that is being used. However, this is offset by the higher protein that it is extracted overall in the process. Some other experiments done related to the time in between harvesting and processing the biomass. So overall, in this case here, we have like this timing between 0 and 12, well, half an hour and 12 hours in between harvesting and processing. And both in terms of dry matter content and crude protein content, we observed the faster we process the biomass after harvesting, the higher will be the extraction yield. Also, we observed that better when we the biomass whole in the field, and then we macerate only directly in the biorefinery. It is also possible to cut in smaller particle size directly in the field, but this will contribute to a higher protein degradation, leading to a lower yield compared to the case where we cut the biomass directly in the field. We also have done some economy techno-economic assessment a few years with some assumptions that we have mainly a production of 6 months per year. This is when we have the green biomass available in Denmark, which is like producing from late May, April, May, until like the end of October. So overall, we observe actually a negative profit for that base case scenario that I showed using biomass, well, the protein for feed, also the fiber for feeding cows, and the brown juice for biogas. However, if we sell the biomass, instead of selling at conventional price compared to the price of the soybean meals, if we sell it as an organic price, we can actually increase the profit here. But mainly other assumptions should be taken into consideration. Here, for example, we have the sensitivity analysis where we compare the biomass, well, the protein concentrate being sold at different prices compared to soybean meal, and if it is sold as an organic as an organic protein, we could achieve something more profitable, but it is highly recommended that we have a year-round production of the biomass, which is not really feasible here due to we cannot have the year-round production of the grass and legumes. So it is, we are constantly checking all the possibilities of application during this off-season period. The status overall of green biorefinery in Denmark is that we could already achieve a good quality of protein concentrate that can replace the soy meal to feed monogastric animals, and this has already been tested here with different pigs. The fiber cake can also be used for both for biogas and also for feeding ruminant feed animals, since it has still enough protein content in the fiber that could feed those animals. However, the yield is still quite little compared to what we expect to achieve. So this is one of our focus now is, for example, enhancing this maceration step where we can actually extract more of the protein in our leaf protein concentrate. We also need to investigate, have potential to investigate different applications for our bioproducts, the fiber and the press cake. And the commercialization of this base case scenario is actually on the way here in Denmark. We have 2 plants that are already in operation. We have BioRefine and Awesomegod. But of course, there are still several challenges to overcome and make the process more profitable. So just field development that we are currently constantly evaluating in our green biorefinery. We actually, as you can see, we have many other applications, not only our base case as ruminant feed, fruit, protein, and biogas, but many other utilizations of our main products. Well, yeah. So in terms of the protein concentration fraction, we actually have this INTERREG project called Green Valleys that is in the Green Valleys 2.0 at the moment, where we actually intend to not only get this protein concentrate, but we are actually intending to have two different fractions of protein. While the green protein is actually the one used for monogastric feed, but we actually have a soluble white protein that have all the further applications. It can be used for fish feed as well as human food. This is a process that we have like the addition of many other steps. So we have two heating steps in this process. And it also requires the utilization of some membrane technologies to make sure that none of this green protein that will be used for feed is in the white together with the white protein. In terms of the fiber, the base case that I mentioned is the use for ruminants, but it can also be used in the biogas plant, as well as different other cases that we have been already tested in terms of thermal conversions using in the pyrolysis for biochar, in the HTL for biocrude production, also in the lignocellulosic biorefinery for the extraction of grass oil, and the application in different production of different biomaterials, for example, insulation and packaging, and the production of textiles from the fiber. And finally, for the residual, the brown juice, the base case, it is the biogas production, but it can also be used, for example, for the fermentation of single cell protein, as well as fermentation of astaxanthin, ethanol, and lactic acid. And it's also possible to up-concentrate this juice via membrane technology, where it makes possible to separate the different valuable organic compounds using micro, ultra, and nanofiltration. Well, thank you again for the kind invitation to this, and I'm open to questions if any.
Yes, we have, and thank you, Thomas. Very well-researched presentation. We have three questions actually from Tommy Lindström. First one, scalability. Are there minimum size of a protein yield process?
Minimum, well,
size of a protein yield process, yeah. Scalability, that's the first question. And second one, maybe I can put together all three.
Yeah, because, well, I'm not really sure how to answer.
Okay.
First,
this is about scalability. Second one, cost of process, suitable for small scale farmers or requires big plants to get good OPEX and CAPEX. And third one, end markets, in or outside the agricultural sector.
Yeah, so our focus it's always on the protein extraction. But yeah, as I showed, maybe it's a way of answering all of them, but the profit, as you can see, it's nearly zero at the moment. And we recently observed that what makes it more attractive is actually the investigation of the other side fractions, the fiber and in the brown juice. So what we have noticed recently is that when you utilize those two fractions for biogas production is when we can make it more profitable. And this study here, for example, is that is showing the base case we use in the fiber for ruminant feed production. And this gives this quite, negative profit. However, I haven't shown here, but we also haven't finalized it. But when we apply the fiber for biogas is where we can have it more profit case. In terms of scale, I have used here a 40 tons per year of fresh biomass, per hour of fresh biomass being produced. I'm not really sure how much they use in commercial scale, but of course it's much larger production. And yeah, maybe not sure about if I'm missing any information. But yeah, we have also interest from both the government here in terms of the implementation, as we already have two. In Denmark has already two of those plants in operation, but also local farmers that are constantly coming and visiting the facility to see what we do over there.
So local farmers are interested.
Yes, yeah. Well, we constantly have this open house. So yeah, local farmers they come and see what has been doing.
Can I ask a question?
Yep.
What would you say, how is in Sweden in this area? It's I think we haven't managed to show that it's profitable enough for companies to wanting to invest or to build a plant. How is it in Denmark? You said there are some commercial plants, but is it like, have you shown that it's enough for them to start business in this area?
Yeah.
Or do you need more develop other used products or?
Yeah, for sure there is a lot of room for implementation. The positive thing is that there is this interest of the government, the Danish government, in terms of the investigation here, and also a lot of subsidies for the implementation of those commercial plants. But yeah, there is still a lot of room to make it the process overall more profitable. This project that I have mentioned here, this INTERREG project, Green Valleys, and there's also this one, Green Improve. This is in a collaboration of Sweden. And then in this one, Green Improve, that have like similar goals. It's in collaboration of one of those two plants that have been implemented here in Denmark. So they are pretty much interested in the separation of those two protein here. So it's a project that started last year. It's a big process compared to the base case where we only have like one stage of the heating and after the precipitation. Here it requires two heating steps and the implementation of some membrane. So yes, we should have room and need to increase the profitability of the process overall, but they are all aware, and yeah, we have been doing this investigation. We have noticed already, we could achieve already the separation of the green and the so-called green and white proteins, but in a smaller scale, as you can see here. Last year we could implement this membrane technology to achieve something higher, but the yield is still low, and this is why we are in this project now.
Okay. Yeah, thank you.
Yep, thank you. And there is a comment, Sindal Biogas on Jutland are starting production this year. This is a comment in chat room. And one more question, there's written, what would be the recovery percentage extracted protein from protein in the raw material of the 15-20% protein yield be? What would the recovery of the 15-20 protein yield be?
I can't see the chat, so it's difficult to...
Yeah, to catch it, maybe.
Yeah.
See, there's a question, second one in a row.
I don't have access to
You don't have access to meeting chat?
I can't see the chat because I have full mode here of the presentation. Which is I think I'm off.
Can we show the
the presentation is
chat? Maybe you can just click on chat.
Yes.
This is you see Daniel Azdini question.
Yeah, I'm not sure what she means by the recovery, but yeah, okay, maybe it's for the overall protein that we have available in the biomass. We intend to go to 15 to 20% being found finally in this leaf protein concentrate. So we aim at extracting around 20% of the protein from the overall biomass. Maybe this is...
Okay, that would be your answer. Okay, anyway, Danny, if you got an answer, okay. If not, you can come back later. We can come back later with the
Yes. Yeah,
you
have my
correct
contact
answer.
information and
Yeah, we could do it. Thank you very much. So far, I don't see any more questions, actually. I think it seems all questions have been covered. Tolle, thank you again for your insights and follow-up answers. I appreciate all questions as well. And if there are no more, so we'll transition to the next segment. Tolle, thank you very much. And nitrogen enrichment of fertilizers. I'm pleased to introduce our next speaker, Trond Lund, and to Applied Norway. Trond Lund is heading the business development activities in N2 Applied since 2018 and has many years of experience previously from the food industry and aquaculture, originally from a dairy farm. He's now very happy to work on solving some of the most important challenges for the farmers and for the environment. Trond, you are up next, please.
Thank you very much. Thank you for the invitation. And first of all, is the presentation visible? Can you see the presentation?
Yes, we can.
Thank you. Okay, yes, and thank you for the introduction. I would like to talk about nitrogen enrichment of fertilizer, as you said. I kind of changed it to manures and digestates to be more clear about the purpose here. And our focus in N2 Applied is developed towards nitrogen, but it has a lot of other aspects. So I'll try to give you a presentation of the technology and also other aspects that is relevant for the circular economy. So this is, of course, a very classic setup, how to feed the growing world population without increasing the emissions and the land use. And that is basically that there is a big need for nitrogen to produce proteins, and that the current world population is fed about roughly 50% from mineral fertilizers produced by fossil inputs, coal or gas. What we do is use electricity, and it is not electrolysis. It is a plasma process that takes air and feed that nitrogen, reactive nitrogen, into slurries. So it could be digestate or farmyard manures. And then we get something we call NEO, nitrogen enriched organic fertilizer. The plasma process as such, I'll come back to. But overall, we have seen that this can reduce to 30% of the global or greenhouse gas emissions. So the number of CO2 equivalents per kilo of milk, for instance, by 30%. And that we can have average demonstrated yield increases per ton of nitrogen applied on about 40%. This varies a bit, and it depends on how you calculate it. The latest Danish trial from Seges shows that 1 ton of digestate from after processing is about 2.5 to 3.5 times more fertilizer value than the raw material. So if you take digestate and then run it through the machine, then the digestate can be spread over a bigger area or grow more crops. And one of the effects of doing this is that we stop the ammonia loss. So normally it's about 50% reduction in what they, in LCA terms, call the respiratory inorganics, but in layman terms, I'd say cut in air pollution. But the scientist will not accept that sentence. So, as I said, the chemical fertilizer is fossil-based. There's a high GHG emission on a global scale. Some mention, or some reports is 3. The latest I read now in Nature was 5% of the world's GHG emissions. But of course, this changes. It's all centralized production. You have to spend $1 billion to start a factory, and it's complex supply chains. What we have seen now, because of certain war situations and geopolitical instability, this is part of the self-sufficiency and a stable system. Without, let's say, available fertilizer, we saw that it becomes shifts in what you produce. Less food wheat and more feed proteins and stuff like that happened in 2022. The other source of nitrogen or fertilizer is from livestock manure or digestates. You have a lot of ammonia. There's high emissions, and it's quite low fertilizer value. You have smell, you have pathogens, and a lot of other issues that we have to care about. So basically, what we say is that a farm system around a cow would look something like this. You would have roughly 50% losses of the nitrogen from the nitrogen the cow eats to what is lost plus what is in the protein, in the milk and the meat. So every year we have to replenish 50% of the nitrogen. This is, of course, a linear system, and what we introduce is a circular system. We actually take nitrogen from the air, we add that into the slurry, and we stop the ammonia and the methane loss. And therefore, a farm with an installation from us will not need to buy mineral fertilizer. Maybe sometimes you need something, or other farms will have to or could export fertilizer. So it's not 100% system, but it could be in many places. So the problems, if you look at carbon footprint or GHG emissions, on a livestock farm, most of the emissions is on farm. I think Nestle has reported 94% of their CO2 emissions or footprint is on scope 3 on the farm. So this is where we need to do things. So what we do is locally on the farm to solve the problem or the challenges. For a small system, it's of course integrated on the farm as a 20-feet container. We're currently producing them, or GEA is producing them in Germany, and we put it just between the animals and the slurry storage. On a biogas plant, it would be when we take the digestate out, and then run it through the machine before storage. So we're not introducing more nitrogen as before the biogas plant, but after or before the anaerobic digester. The technical thing we actually do is that we use the plasma to split the triple bond in the nitrogen, and this is where we are. It looks like a lightning strike, but it's continuous and it runs. It can run for continuously, basically. What we create is a gas which consists of NO, NO2, and some other components. And this is what we absorb into the liquid slurry. And when you absorb NO gas and in a way meet the NH3 or the ammonia or NH4, you get ammonium and nitrates. So this is what does the trick. And if you look at this is a typical, it's more like a farm scale digestate. And the brown part is the organic nitrogen, which consists of straw and different proteins and others who are not really converted. The rest is the ammonium N, and on top here you would have a potential loss on storage and spreading going forward, because the pH would often be above 7, or say from a biogas plant it would be more between 7.5 to 8.5, so or even higher. So most of the ammonium will be volatile and would be very happy to escape. When we treat the digestate or the manures, we add nitrogen, so that when we take a sample or an analysis, we will have pH below 6. It would be below 5.5 in most cases. And then everything, there's no ammonia, but everything is ammonium. It's stable, and we've added nitrite and nitrate. And this is efficient, and this fraction is what means that 1 ton has 3 to 5 times more reactive nitrogen, and is therefore a very efficient fertilizer. So our company has invested, I would say, roughly 15 million euros in scientific trials, supported also by national, in Norway, National Research Council, and in the EU by Horizon. We've done around 50 field trials, always in plot trials and with serious institutions. See some of them above there. And we've had operations pilot scale in around 20 different farms. And now we are rolling out. There's units going into Germany and Netherlands right now, and Scotland. So that's how it looks. I could say a little bit about what we've done. On the biogas, we spent a couple of years with the Folum, by Henrik Møller at Aarhus University, where we continuously measured the emissions of ammonia, nitrous oxides, methane, and all that. On those trials, we're actually seeing that the storage is an ammonia sink. There's less ammonia in the air out from the storage than what came into the storage. It's a quite, let's say, curious aspect. We've also been to more biogas together with Rice and SLU in Sweden, basically focusing on the nitrogen and phosphorus balances on different fields, and of course tested the fertilizer. On the scientific side, the top here is normal slurry spread in say band spreading. So it means that it's put down on the ground. It's not injection, but it's what we call a low emission spreading method. And on the bottom, it's chemical fertilizer, and the brown is the NEO. And we see we have a little bit lower than chemical fertilizer in the beginning, or mineral fertilizer, but basically following the same path. So reducing ammonia emissions is of course cool, but you're not really paid for that. So the important thing is the yield results, where we see that if you compare our plasma slurry or NEO with untreated, we see about a 43% yield increase on this one, where you add the same amount of nitrogen per hectare. But more importantly is the nitrogen use efficiency, where you see that we have a higher, or that plasma gives more proteins to the kernel. So having a high nitrogen use efficiency means less nitrogen is ending up as pollution. Basically, you have to keep as high nitrogen use efficiency as possible to have a circular system. But this is also good for the climate because now we've had many years. It started actually at RISE in 2019, showing a complete elimination of the methane formation. So here you see on the left, there's 3 graphs from 21, 22, and 23 on normal slurry during 70, 80 days. And on the right side, you see the NEO. And I'm not saying that it's a sink, but and it's very small numbers here. It's this is like 0.3 grams per hectare, no, per ton, while here we have 1,000 or 60 and 300. So it's small numbers, but basically it shows that we have a negative development on the accumulated methane in the tanks. So we are absolutely eliminating methane in the NEO. And this is quite important for some, say every biogas operation that is, and there's a lot of people that knows much more than me on this, but what we've seen from the, if you have a 30 or 40 days retention time in the anaerobic digester, in the AD, you still have methane formation in the digestate. And with our technology, we absolutely stop that. So improving the footprint. What was then done by Arla and LCA, or 2DOT's LCA consultants from the University of Aalborg, was that if you look at N2 applied and biogas combined, you would get a 36% reduction. So the best option is to do both. But basically, it's the methane that is the main point, and the chemical fertilizer replacement is secondary. But stopping ammonia is only a secondary effect on nitrous oxide. Last point I want to mention is that, and I think this is not always communicated that much. These are the Rodhamsted trials that started in 1843. Back in 1866, they started to add nitrogen, and in 1888, nitrogen and phosphorus and calcium, so NPK fertilizer. And they compared, there were of course a lot of yield trials showing that the chemical fertilizer works perfectly. But here they have taken the measurements of soil organic carbon actually since 1843. And what we see is that with a pure chemical fertilizer or mineral fertilizer system, you cannot, in these trials, get much above the low 30s in tons of carbon per hectare. If you add farmyard manure, and I'll propose that the same is with digestate, you can actually come up to levels above 70. So more than double the carbon in the soil. To have a resilient food system, we really need to have organic matter also on arable land. And I know that the European Sustainable Phosphorus Platforms first, top of the list is area planning on how to solve these issues. So making sure that you have organic material going out on arable land is quite important. And I think if you have a high carbon content in the soil, you will have a higher resilience towards floods and droughts. And that will also reduce the runoffs. So we're trying to prove this on towards the fjord, Oslo Fjord nitrogen problem, or the Trondheim Fjord and others. It's really important for the coastal ecosystems that we keep the nutrients in the farm system and not let it go run out in the rivers and the streams. So organic matter is necessary or digestate or farmyard manure is necessary to use on more areas than today, basically. It's a bit political statement, but it's quite important to build soil carbon. So to sum it up, we are doing more things than one. of course, we're empowering the farmers to produce their zero emission fertilizer on the farm, well, depending on the electricity carbon footprint. This is a chemical fertilizer replacement. It improves crop yields, nitrogen use efficiency, and can add to the soil health and water retention. We follow the UN United Nations targets of what they call white nitrogen. We have to recycle reactive nitrogen onto the farm system. All emissions becomes pollution. You have to do it on the farm or on the biogas plant. You have to make sure that the nitrogen and is stable. And as I haven't really mentioned, when you double the nitrogen and you still fertilize by kilos of nitrogen per hectare, then you also halve the phosphorus input. So you have a more flexibility when you have a high phosphorus load in the system. I failed to mention this, but it's an important aspect. And then, of course, as I said, we reduce the carbon emissions by stopping all methane emissions from slurries, and that is quite important. And of course, if you stop the methane emissions, you also keep the carbon in the slurries. Yeah, I think that was enough. We're 60 people. We're in Norway and the UK and the Netherlands, and we're about 60 people. So just a little bit of ourselves. Thank you.
Thank you very much. Well done. Insightful presentation. We have questions actually. Does the stabilized nitrogen mean decrease of smell?
Yes, you don't smell it. That's thank you for that question. Yeah, we stop. We inhibit the smell of different things. We've just launched. It's actually being published in June, but we sent it in this weekend. A 3-year study on where we prove that we hygienize the slurry. So that means that we have stopped or very high kill rate on E. coli, Salmonella, and Ascaris eggs, meaning that it is a fully hygienizing. So now that's an important thing, and it's the same mechanisms. That's the same mechanisms that stops the methane formation, but also scatol and other things in the smell. So yeah.
Nice. Second question: how many kilowatt hours are needed to produce 1 kilogram nitrogen and 2 applied systems?
It depends a little bit on how much auxiliary. So it depends a little bit on the system. So because we do use pumps and compressors and others. We are working with the universities around in Antwerp and others, and our best systems are getting quite low. If you buy a farm system today, the plasma would be something between above 50 kilowatt hours per kilo of nitrogen. But you have to count in the removal of the losses. So if you have a base case that says you don't have any emissions, then it's much more expensive than buying chemical fertilizer. So it depends on what you compare against.
Okay. And your system, is it affordable, suitable for, let's say, small scale farmers?
The business case is totally dependent on energy price. So if you have so what we say is that you need to have control. So it should preferably be in a renewable energy system where you have renewable energy on the farm. Secondary is if there's any payment for the sustainability. So we are not competing against mineral fertilizer from fossil fuels, but on other aspects. But we can find business cases that works. But preferably, the places we add machines now is, for instance, to Unilever and other big ones who actually want to reduce their carbon footprint and therefore pay for CO2 reduction directly. Then it works. But for a normal farmer who is not getting paid for any sustainability, it's cheaper to buy a bag of fossil-based fertilizer.
Okay. You mentioned 60 highly educated professionals in your company. Do you collaborate with universities or headhunters to teach or recruit them? How did you find them?
Sometimes, I mean, we've run projects with, as I showed you, a lot of universities and institutions, and some are, and that's of course a good recruiting arena. But basically, we recruit just ourselves, and then it gets a we have it's not too hard to get people to start here or in the UK or in Holland.
Okay.
So
you mentioned advantages of your system, but could you name some disadvantages of your equipment and device so far, let's say, challenges to tackle?
Yeah, there's today, I mean, this is early. It's a high, relatively high investment cost. If you look at the farm system, where well, not per ton of carbon, no, per ton of feedstock, we are sometimes between 50 to 60% of what a biogas plant costs on a farm. But so it's still quite a high cost.
Okay.
Yeah, but
okay, I see. High cost. Remark, it is not organic matter alone which builds soil carbon. It is living plant roots which use organic matter that build soil carbon from root exudates. Root systems keep the soil structure and aids in resilience. This is a remark. You have to add something?
Absolutely. And I said that initially that there's more to this than just the Rodenstedt trials. The Rodenstedt trials was just a very simple way of saying that soon 200 years have shown that there's an advantage by adding organic matter to the soil. It could be compost or anything, but that was my comment. I'm not trying to be a soil scientist, so it's absolutely right, or she.
Once again, thank you very much for your presentation and follow-up answers. If there are no further inquiries, seems so, we will now proceed to the next agenda item. Our next guest, let me introduce Sampo Järnefeld from Soil Food. It's a joint Finland-Sweden venture. Soil Food is a circular economy company whose goal is to replace virgin raw materials with recycled materials in large volumes and quickly. This is very important. So, Sampo, you are invited to take the lead.
Thank you very much for the introduction, and very nice to be here. Also, thank you for having me here. As said, my name is Sampo Järnefeld. I'm the Chief Commercial Officer for Soil Food Company, and we are founded in Finland, but nowadays also based in Sweden. I was thinking a lot and discussing with Inga about the topics for this presentation. We do various different kinds of businesses. But shortly about Soil Food, we are still a pretty small company. We are only approximately 30 people in Soil Food at the moment. That being said, our business logic is relying a lot on subcontractors and contractors, and those we are cooperating with over 100 persons and employing over 100 persons through our subcontractors. The topic here is largely based on rather business logics than any advanced technology. The business idea for us is mainly we take raw materials from different sorts of industries, from paper and pulp mills, biogas plants, food industry, etc. And we identify identify the value for possible customers in agriculture, and nowadays also in industry. So we actually are developing new products and inputs for industrial use, mainly chemical products. Just a moment, I'm trying to change the slide here. Yeah. So the topic here is not so much about the processing of the products, but rather than the idea of how to utilize different sorts of raw materials, and how we have identified the value for different sorts of raw material. There are lots of fancy important words in this slide, but if you think about the background, our background, it's highly based on value, and you could even say ideology. But having said that, even though you have good values, we want to replace an ideology. We want to replace as much virgin raw materials as fast as possible. But the way I see it, that the business logic is also a pretty good way of measuring whether you're doing it successfully or not. We've been founded 2015. Our operation started in 2016, and nowadays our revenue is approximately 10 million euros a year, and we've been profitable from the year one. And it's mainly based on the business logic, how we do it. So rather than developing highly evolved processes to process different sorts of raw materials, we've actually been more focused on identifying or picking up the suitable raw materials from which we can identify the value for the farmer. And obviously, there always needs to be some refining, and that's what we do as well. But we're trying to keep the costs as low as possible, of course. And in our cases, it means that we have no rules and walls. We have limited amount of machinery, and we try to utilize as much the facilities from the factory facilities where the raw materials actually come from, and together with our customers try to identify the way to process the materials as required, and quite often it requires also mixing and blending other materials from other sources as well, but we're trying to keep this as minimum as possible. And the idea of why we're not investing so much on walls and roofs is basically because when you do it, you are also tight into that spot, and you need to make sure that you actually get the costs covered, and it also a little bit limits your possibilities to what you had. That's at least the case where soil food is now. Having said that, the market at the moment is surely going to that direction that you can neglect R&D. It's becoming increasingly important to us as well, and we've been investing on research and development. So far, it's approximately 5 to 10% of our yearly cost or yearly budget has been on research and development. So you cannot skip that. But it's becoming more clear that the solution that the previous presentations have shown here is in a way the right direction that where this industry needs to go in order to build up the value. Okay, but Just a couple of words and notions we've made during the years from the market. First of all, when we talk about we're making business with circular bioeconomy, and it's easy to talk about it if you don't have to use it in practice. But there are lots of certain limitations. I'm sure many of you are aware of, and mostly it's have got something to do with money. In general, when people are talking about circular bioeconomy, you know, it's just like it's often forgotten that it's mostly local or aerial business. The raw material that we are being processing and delivering to our customers, you know, we're working in Finland and Sweden, but always the business is more or less local, meaning we are operating in, for example, in southeastern Finland, and the market area for different raw materials might be like it's southeastern Finland. Like depending on the raw material itself, whether it's biogas slurry, the distance from the factory is 50 kilometers, or with other products, for example, limes in Finland, it can be 200 kilometers, but still it's very limited and local, and that's something that people tend to forget when talking about circular economy. The other thing, like, is to which extent you should refine your products, and it's actually an essential question. It's about providing value for the customer and getting his price out of it, and with which cost. That is the question. The products that we are demanded the most is organic granular fertilizer, which we don't have, and you can count on us, count on it that we've been investigating this possibility many times and making the calculations with different sorts of raw materials, and we just can't add it up. We cannot get the math working, where we should actually invest a big pile of money to refine different raw materials, whether it's cow manure or anything else, so that it would be profitable business after the investment and after the operating expenses. Then the other thing is that many of the raw materials and these circular bioeconomy products available with low level of refining, they are not feasible for the farmers to use. So that's the other limiting factor in this business. So if you think about, for example, biogas slurry, which is pretty simple to comprehend and understand the logic, at least in Finland, there are limited infrastructure with farmers who could actually store and utilize the product. So actually, in those cases, you need to provide the services as well. It's not about the product only, but it's about the services for the factory and for the farmer. So that is the business you need to build on. And then one thing is also, like, we're talking about different sorts of products. Really interesting presentation from the previous two. Thank you for that. The thing to notice is that the products are not comparable as such, and they don't need to be. It's more about like identifying which product to use where and for what purposes, and what is the value that it can provide for the farmer or the environment, or other purposes it's aimed at. And this leads me to the actual thing we're actually doing in soil food, and I cannot talk about it without at least shortly talking about a little bit about the soil health. So I'm a farmer myself, and you can say that when it comes to crop yield, there are two limiting factors that compete with all the others, and the first one is the weather, and there's pretty much nothing you can do about with the weather. You just take it as it is. But the second one is soil health, and soil health provides yield and also profitability. Soil health in as an essence is actually more important for profitable farming business than, for example, fertilizers or pesticides or any other inputs. It's about the soil health. And there are actually only there are two things that you cannot skip when talking about soil health. The other one is that you need to have a good crop rotation and also working drainage or water management. Those are the two essential things that farmers need to manage in order to achieve anything with good soil health. Good soil health is really important. Like this is obviously it's been investigated and by many people. This a presentation from Thomas Keller and his team from Stockholm University like 12 years ago, but I think the basic message here applies very well. What they found out was that the bad soil health, you can identify from these two pictures, you can identify which is good soil and which is bad soil. And the effect of bad soil to crop yield is in conventional farming is 30%. So basically that means that before the farmer has done anything on the field during the season, with bad soil, 30% of the crop yield is already lost. With organic farming, it's 60%. And the economical value is based on like prices we have for wheat in Finland last week, and the crop yield for conventional yield, I guess I evaluated like the good crop yield would be 7,000 kilos, and for organic farming 5,000 kilos. And counting down from that, the losses you have based on the prices we had 1 week ago, you're losing in conventional farming with bad soil, you're losing 480 euros less income per hectare. If you have 10 hectares of bad soil, it means almost 5,000 euros. If you don't do anything for the bad soil and you still have the 10 hectares, in 10 years it will be almost 50,000 euros, and it's all away from your income or from farmers' income. So this is basically how we motivate the people to think about the soil health and try to do something about it. And I'm not here claiming that soil food is to fix them all, because soil health is complex area, and I said there is nothing that can replace good crop rotation and good drainage. Those are two essential issues you need to take care of. But then there are other things you can do as well, and that's where we come along. This product here, which has been spread, is actually from my fields. A couple of years ago, we're spreading a product named soil improvement fiber or nutrient fiber. There are different types of soil improvement fibers depending on their quality. And it's a product we actually, the raw materials come from paper and pulp industry. It's mainly wood-based side streams, fibers that needs to be mixed and stabilized. And stabilizing is done either by composting, or you can also, and what we do as well is lime stabilizing the product with either calcium hydroxide or calcium oxide. The application rate is approximately, it varies from 20 to 50 tons per hectare. If you are having a fiber with no nutrients, it can be even higher, but then there are other factors, for example, nitrogen you need to take into calculation. But with the product here I'm talking about here, the nutrient fiber, the application rate is approximately 20 to 50 tons per hectare. And the amount is evaluated based on the product itself and also the conditions on the field that should be used. It's not a yearly product, it's not a fertilizer. That is important thing to say. This is not a fertilizer. It's a soil improvement fiber, which you apply once per crop rotation, whether it's 4 years or 6 years. It's pretty okay. And the idea is that actually the organic matter in the product start decomposing in time, but still after you added the fiber, you get organic matter. The microbes start to eat it, and you after let's say after 5 years, there's still 40% left, and then you can add more, and it's like step by step increasing the soil organic matter in the soil. Expenses for the farmers currently is approximately this like rough estimation 180 euros to 300 euros per hectare. And what you actually doing by applying nutrition fiber, you are in a way recharging the soil with nutrients and carbon. Basically, there is always if you add, let's say, 30 tons of nutrition fiber, there's always a certain amount of water, and 58% of the organic dry matter is carbon. So depending on the amount you're spreading, you can add, let's say, 5,000 kilos per hectare carbon per one time, or even more, which is by far the fastest way of actually that we've gone by so far. This is the fastest way of actually adding full organic matter to the fields. There are other good methods to add soil organic matter, like having cover crops and having grasses in your crop rotation, etc., etc. Those are all things that add carbon to your field and organic matter to your field, but none of them is anyway close to the amount we are able to do here. While you're adding the soil improvement fiber and all the carbon, you're actually also adding nutrients which are binded to the organic matter of the fiber. It's varies. It's usually the amount of nitrogen is 100 to 250 kilos per hectare with those amounts added. There's phosphorus, there's calcium, there's calcium and zinc, and also some micronutrients. The amount varies depending on the product. But the important thing here is to understand, as I said before, this is not a fertilizer as such. It's recharging the soil. So let's say that from that amount of nitrogen after the spreading for the next season, let's say approximately 15% will be plant available. So all the nutrients will become plant available while the organic matter is decomposing, and approximately 40% of all the organic matter will stay in the soil for longer period, let's say 20 years or even longer. So there will be multiple benefits. This is a product that is good for the industry. It's good for the industry because at least many of the factories have been burning this material, this side stream before, but in many cases, not in all cases, but in many cases, the energy value is pretty low. So it's actually more beneficial for them to our business logic to pay us so that we will take care of it, and after that we will take care of and handle all the raw materials, do the mixing, do the refining, and we will find the customers, and also provide services with spreading and all the consulting for the farmers, because these are kind of products that you really need to know what you're doing with. And for farmers, they need to pay some, but they get the benefit. they get the recharged soil, and especially in Finland, with the southern part of Finland, we haven't had livestock in decades, and it's really starting to show in the soil structure that the organic matter is losing. So they're getting the benefit from this, adding the soil organic matter. In practice, it means better water holding capacity. It means better calcium exchange capacity. That is meaning the nutrient holding capacity. And it's also food for the microorganisms. And most of the soil improvement work is done by the microorganisms. When you're adding such product as this, you're actually boosting the microbial activity in the soil, which eventually will bring you the benefits of better soil. From environmental point of view, it's also reduces drastically nutrition and carbon leaching. We have several research done where the phosphorus leakage drops after the first year. During the first year after the spreading, the phosphorus leaching has been minus 80%, so 80% less than prior to the spreading. And even after 5 years, it's still like minus 40%. So there are significant benefits, and especially with Finnish archipelago, this is one of the solutions that we are starting to use to improve the Baltic Sea Baltic Sea conditions, especially in the Finnish archipelago. Yeah, I said this is just a quote from one of the researchers and his team, Kim Morasa, who've been on this topic for many years now. Sorry. Another example with you might say with similar benefits, not the same benefits but similar, is the recycled lime products. The Finnish soil is by nature low in pH, causing many disadvantages. The normal pH, if you take like with the long way history, when you take the forest for field use, the pH is somewhere around 4 and something. But obviously that has been problem forever, and the Finnish farmers are really accustomed for liming their fields. But the limes that have been using mostly are like virgin mined limestones, calcite and dolomite, etc., etc. And we are replacing those limes. Those mining activity obviously causes environmental problems and carbon leaching, carbon dioxide leaching, and that we are replacing those limes with recycled limes from different purposes, from different industries. There are variation with the raw materials, with the lime side streams, but in general level, we can say that we can replace 1 ton of we might say traditional lime. We can replace. We can replace 1.5 tons of traditional lime with 1 ton of recycled lime and still get the same pH results. And it quite often comes with benefits as well. But when you're using the mined lime, the carbon footprint is roughly 200 to 400 kilos carbon dioxide equivalent per ton. And if you're using structural limes, meaning like calcium hydroxide or calcium oxide, the carbon footprint is as high as 1,000 to 1,200 kilos. So we are able to replace that, and actually our products cause 99% less emissions, especially with the structural limes. than those mined and burnt limes. Depending on the lime product itself, it has different kind of advantages for farmer. With calcium oxide or calcium hydroxide, you can actually improve your clay soil structure. It's a chemical phenomenon that happens, but you need to have at least 20% of clay content in the soil or higher. But another interesting is that we are able to add phosphorus to the lime. And since the farmers tend to use limes anyway, and the phosphorus is expensive, it benefits them to do the liming and some of the phosphorus fertilizing simultaneously. So they can actually, with the limes we have, they can decrease the need for other phosphorus fertilizers. The phosphorus in our limes is 95% plant available. Not all of them is soluble. Some of them are soluble, and some of them are like binded with calcium or magnesium or other compounds. The amount of phosphorus varies depending on the product. It's from 2.5 kilos per ton to up to 7 kilos per ton. So if the normal amount of lime you add to your soil is, let's say, 4 to 5 kilos, you can say you can easily get, for example, 15 or 20 kilos of plant available phosphorus. Now there is also like a variation based on the solubility of the phosphorus. None of them is water soluble, which is actually great because water soluble phosphorus tends to make very strong attachments in the soil water with aluminium and iron, which is abundant in Finnish soils. Instead that having the soil water soluble phosphorus, it's usually at least half of the phosphorus is like easily plant available, but not water soluble, and the rest of the phosphorus is then available, let's say, within 2 or 4 years after the spreading. So this is just another example of thinking a little bit differently. Rather than thinking this product only as a lime, it's also something that you can provide phosphorus fertilizing value. Okay, it seems that was this last slide. I thought there was one more. I'm sure I might have extended my time. Sorry about that. If you have time for questions. Contact your mic is
Microphone is muted.
You mean my mic? I said kiitos, Sampo. Kiitos. Kiitos
No,
for your
kiitos,
time.
very well.
Thanks for your time. We have a couple of questions, actually. Question to Sampo. What are the advances with wood fibers compared to the use of biochar? Have you considered biochar?
We have considered biochar, but producing biochar, basically biochar is great, and it has lots of benefits for the soil. The downside with biochar is that it's quite expensive to produce, and basically I would say that from the market point of view, the farmers are not ready to use biochar as soil improvement material because it's cost, let's say, 300 or 600 euros per ton. And for biochar purposes, we need to have a program or process where the farmers actually benefit from binding the carbon in the biochar. We tried that. We didn't try. We made that also with the fibers because it's pretty easy to calculate how much carbon is sequestrated to soil through our fibers. But the market is, let's say, unpredictable, and we had some succeed, but as said, we can promise that 40% of this carbon will be sequestrated in the soil for 20 years.
Okay.
And for many players in the market, 20 years is not enough.
We can ask about the use of biochar to our next presenter, but but so far, next question: have you noticed an yield increase or decrease the first years after application of fiber? Reference the experiences of application of uncharged biochar compared to charged biochar.
There are different, but the main issue here is to actually identify how to use these different sorts of products. If you have nitrogen charged fibers, you could say that it's self-sustained. There is basically enough nitrogen to start the composting process, and in that way it won't be away from the plants, with the exception that you need to wait some time. Like our experience that you need to wait, let's say 2 to 4 weeks, sometimes even a little bit longer, so that the microbial boost, the peak is over, and after that you will actually start to get also the nutrition benefits coming out of it. But there is I don't have the picture here, but there will be a dip with available nitrogen. And then if you have a fiber that is not charged with nutrients, then you need to make sure that you get the nitrogen from somewhere else. And in those cases, it's a pretty good product to be used combined with, for example, slurry or sludge, which easily causes nutrient leakages after you use it, and especially at least in Finland, when they're spreading it also during the autumn, and after the spreading there will be all the autumn rains, which will cause big leakage from the fields. So actually using these kind of fibers that are not recharged with nutrients already, they can actually harvest the nutrients from the slurry or sludge, spread it on the field.
Thank you. And last one question: the content of nutrients in the soil improver is of course not constant, as it depends on the raw material. Do you have data on the dynamics of nutrients in the soil by year?
I'm not sure. I'm quite sure whether I understand the question quite entirely, but yes, we collect data. We have from the product itself, because it's a side stream. There's also like, even though we take it from the single, if we would take it from a single source, there will always be variation, and that's why quality control is really essential. And we're doing it very actively. We're making basically weekly analysis from the products that we are delivering for the customers, so that we can make sure that we are within certain limits and that the quality control stays on track.
Sampo, thank you very much. Kiitos.
Kiitos.
Yeah, that was really well done. And if you have more questions, you can come back later and ask Sampo some questions. Thank you very much. And we have to move on. And our next presenter, Paul Nielsen. And this topic is about pyrolysis and development of biochar from different biomass fractions. And Paul is a WOW representing WOW Green Metals. He is Vice President, Innovation in WOW, developing industrial pyrolysis processes to valorize organic waste. Board member in European Biochar Industry Consortium as well. Paul, stage is yours.
Thank you very much. Happy to be here. Let me know if you can see my screen.
Yes.
Good.
Yes, we can see.
Yeah, my name is Paul Nielsen. I'm doing development of processes for making biochar from different organic wastes at the moment. WOW is let me see. WOW is a Norwegian company. We have more than 200 people. Our main business has historically been to provide wastewater treatment systems and waste management systems for cruise ships. So we have had a lot of activities in Turkey regarding the major work there on cruise ships. We have some 70% market share on wastewater treatment and on these cruise ships, advanced wastewater treatment. Lately, we have also developed pyrolysis systems for cruise ships to make biochar out of the organic waste on board the ships and use some of the energy in the waste for the use in the ships. In addition, we have now the portfolio of pyrolysis equipment from France. We have bought ETIA. They have developed these electric heated screw conveyor pyrolysis reactors. So we have worked with them since 2019 and industrialized these systems and are now building larger facilities with them. And last member of the family is CHE Evensen, a Norwegian company specialized in industrial heating applications in ovens and also in rotary kilns. And together with them, we have developed a very large pyrolysis reactor that we are now deploying for the larger industrial scales. Why pyrolysis? Pyrolysis is it is a thermal treatment of biomass. We heat up the biomass without oxygen present. Thereby, we are able to split the organic molecules into smaller parts and provide biochar, which is a very carbon-rich stable structure. And the reason we do it is to take some of the carbon out of the circulation and bring it out of the atmosphere to improve the climate. So you get the biochar, almost 50% of the carbon in the biomass could be captured in a stable carbon fashion. Biochar, we like to call it a hotel for microbes, and it's a battery for nutrients. If it's for a soil application, we'll refer to the last speaker. We have been significantly engaged in waste fractions of biomass. There will be a fight for biomass, and we need to recircle as much as possible of the organic waste fractions. And typical fractions we have looked on is wood residues, garden waste. There will be sewage, of course. There's a lot of nutrients and carbon here. Residues from biogas plants, food waste plants, demolition wood, and so on. The main reason is to bring the carbon out of the atmosphere and to sequester carbon. And in the European Biochar Industry Consortium, we have been working very hard now to prove the stability of the carbon in the biochar. And we have teamed up with petrologists and geologists, in particular with Henrik Pettersen and Ahmed Sanai from Aarhus University. And we have shown that the larger fraction of the carbon in industrial biochars will possess properties of carbon structures that is geologically stable. So this is an example of some newly made biochar. This is 290 million year old biochar that is found in the Earth crust in Australia. So we can take the carbon out of the atmosphere through photosynthesis and biomass and really make it carbon dioxide removal methods. Doing circular economy and recircle organic waste may cause some challenges. It's not only nutrients and carbon in the biomass, it may also be a lot of organic pollutants. And this is just a recent example from Astrid Solvåg-Nesse. She defended her PhD thesis recently. She looked on the organic pollutants in a variety of biomass waste fractions, and there were surprisingly high amounts of these unwanted pollutants, also in what you would reckon as pretty clean waste fractions. We have done a lot of research in this topic lately, and we could find even organic pollutants in the more persistent pollutants in clean wood as such. Paper mills also have some issues in Norway. Water streams, downstream paper mills possess the highest levels of pollutants of PFAS, for instance. So we have shown that we could really eliminate organic pollutants by this high temperature pyrolysis, at the same time contain some of the nutrients like phosphorus and such, and sequester carbon. Biochar, produced by putting biomass into a reactor, heat it up, split the molecules into a gas fraction and to a solid biochar fraction. The gas fraction have some condensates, oils, acids. They could be further processed. We have delivered plants that take some of the bio oil as food grade food additive, as a liquid smoke, as we call it. Smoked salmon is maybe not hang over fire. It is often added with this type of liquids. Woody vinegar is another example of how you could refine some of this through the pyrolysis systems. The gas could be used for heating purposes, electricity purposes, or even split molecule further into methane, hydrogen, and such. The applications of biochar up to now has mainly been in agriculture. It's a lot of benefits. We were talking about this here. So avoid emissions, sequester carbon. There are a lot of benefits. It's used in urban areas, in Sweden in particular, Stockholm model, where you use the biochar together with gravel, and then you have nice structures where biochar sits in between the gravel that has the load-bearing capacity. You could have water-holding capacities, and the biochar could also possess a nice sorbent for pollutants. More contaminated biomass could still be used as biochar into construction materials, and we see increasing activity in using biochar, for instance, in cement and concrete. So there is also a way to sequester carbon from contaminated organic wastes. More sophisticated in polymers. This is I think it's the walls of the facade of the Audi corporate building, where they have put also biochar into the matrix of the panels. We have a long time developed biochar for agricultural purposes with our company in France. First, to get certification for what we call a water retention biochar, where we have optimized clean wood feedstocks to make the biochar as good as possible in water holding capabilities. And there are some examples here where you see what happens with your flowers in your window if you leave for summer holiday and you forget to add your biochar in your pot. You will meet this one. So the more biochar, the better water holding capabilities in this. And this has been used for entrepreneurs to blend into different soil mixes that you could buy which are with magic names because it's magic effects. So this is so. We have the 3 pyrolysis models. One is the microwave assisted system, which we now put on cruise ships. We have put it on the biggest cruise ship in the world, left from Turku in January this year, now in the Caribbean with 10,000 passengers on board, and we make a ton of biochar per day on board that boat based on the organic waste on board the ship. The electric heated screw conveyors typically have a ton of feedstock per hour. You could produce 250 kilos of biochar per hour in this machine. It's electric heated, very well controlled. So we have very accurate process control and can get the good biochar quality. The pyrolysis gas is used for heat purposes normally, and we put it to a boiler for steam production. And then the last member of the family is the big machine we now have developed. It's ready for deployment, and this has a 5-ton capacity. So this can produce more than 1 ton of biochar per hour. And we see now a huge interest in the industry to these larger scale facilities. And we are, as we speak, developing projects in Norway on demolition wood and in US on wood residues on these machines now. This is an example from Helsingborg, where they take garden waste and produce. This is the reactor. This is the pyrolysis gas coming across to a boiler that produces hot water for the domestic heating, and the biochar will go for soil improvement. In Switzerland, with Philip Morris, biochar is produced from pallets, from cardboard packaging, from organic residues from their tobacco production, and the gas is used to produce steam to offset their use of natural gas. So this is a way to save CO2 emissions and also beneficially use the energy in the waste and also produce carbon for sequestration. It's a versatile piece of equipment, and it could also be used for end-of-life tires. So we could recover carbon black in the tires that could be used for new tires. So it's part of the circular economy, even though the carbon in question is not biogenic, it's more fossil. And then what is a lot of interest at the moment is the sewage sludge pyrolysis due to phosphorus recovery, but also to eliminate pollutants. In Japan, this is an example from Japan with sewage sludge, where we have worked with them for 3 years testing in order for them to the Japanese water authorities to approve our equipment as treatment method for sewage sludge in Japan, which is good. So, and one of the reasons for them to engage in this, the authorities, is also that they import a lot of phosphorus, and they see they have to recover phosphorus. The international situation with China, with Morocco and so on, that possess and Russia would possess most of the phosphorus resources, makes it hard and to have a reliable import of this, so they need to do recirculation. And this is also part of these stricter rules and regulations you will now have in EU with the Urban Wastewater Directive, requirements for recovery of nutrients from wastewater treatment plants. And in EBI, we have put a white paper on sewage sludge biochar production, and Helmut Gerber from BREC have calculated sort of the greenhouse impact on recovered phosphorus from sewage sludge based on traditional methods, which all comes with some huge variability in the recovery rate of phosphorus, but also the climate impact. Biochar would be climate positive because we sequester the carbon also in the sludge. Biochar for soil improvement. It's been a lot of analysis. This is an example, an old example from Hans-Peter Schmidt and Claude Kaman, where they looked upon all of these effects reported at that time. It must say that this was in 21. Since then, a huge number of new publications has come along. And you can see the positive effects of biochar from the different publications. These are negative effects, which is good because you reduce leaching and emissions, and you could also bind up heavy metals by this surface affinity of biochar to the heavy metals. Another interesting topic is to use biochar also for health improvement. There are a number of papers looked into this, where biochar is used for different types of soil pathogen control. We are running a cool project now, two cool projects with the NIBIO in Norway. One on barley and wheat nematode issues. So we had a good field plot last year without any remediation methods, and this year we will apply biochar to these to see how that will affect the nematode production. We will do that also with carrots in this case. So it will be exciting to see how this comes along. We have a very nice experimental test setups, so we can do a lot of pyrolysis of various materials. We have tested heavily together with NGI, NTNU, and NMBU, Lindum, and we have the different waste fractions. We have done pyrolysis. We have analyzed the fate of organic contaminants in particular, and we have also seen how biochar can be used as a sorbent for the same pollutants in question. We also have tested how bio-oils could be converted to biomethane, so on and so forth. And the last research we have done, which was presented this week and is also now just accepted in the paper, I would like to put attention to this very nice work from Marjorie Morales. She looked at raw soil sludge, and we had analyzed a lot of organic contaminants, PFAS in particular, which is the most persistent, stable, toxic, very mobile. So we documented that we could eliminate all of these pollutants by pyrolysis. So we measured the content in the biochar, in the flue gas from combustion of the pyrolysis gases, and also from the applications. So we looked at the destiny of raw sludge, what to do with it. Should we do a traditional anaerobic digestion? Should it go for stabilization? Should it go for land application? Should it go for incineration or pyrolysis? And so on. So all of these combinations were looked upon in terms of how the degradation of these pollutants were, the removal efficiency, and also the fate of the residual amount of pollutants in air emissions, in water, and in soil. So a very thorough work based on hundreds of hours of running the pyrolysis equipment as well, and a lot of analysis from various labs. And then she was able to quantify the ecological impacts of this, and also the greenhouse assessment. So go into this system and have a look. And what I will say is that the conclusion is the best solution pathway here for sewage sludge with these contaminants, and all sludges will have some of them in variable degrees, would be no digestion, pyrolysis, and biochar used as a sorbent for soil improvements. The reason for this is also the sensitivity to methane leakages. Methane is 85 times more aggressive than CO2 in a 25 years perspective. So just 1 to 2% of methane leak would sort of offset the benefit of the methane production in the first place. So this is also part of this. So this is examples of what we are doing in our company regarding biochar development. Thanks for your attention.
Paul, thanks for your expertise and sharing the time with us. And we have a questions actually. Can you describe how the phosphorus recovery process is done in pyrolysis of wastewater sludge?
Yeah, it's quite simple. The phosphorus just follow the biochar. So the recovery process is actually to apply the biochar back to the soil, as where the phosphorus is included. Depending on the sludge process in the first place, and depending on the process temperature of the pyrolysis, you could have some variations in plant availability of the phosphorus. But the recovery is high, and the tests that has been done has shown the best example I've seen is that you have some 90% of phosphorus uptake in the plant compared to mineral fertilizer for the same amount of phosphorus. But it could be, for the worst biochar, it could be less of course.
Okay, thank you. One more question. It goes like this. Have you tried inoculating biochar with IMO, indigenous microorganisms, before distribution on field sites?
I have not, or we have not, but I've seen a lot of research done on blending. This standard would be to blend with compost, but to put in some active organisms, of course, as I say, it serves as a hotel for the microorganisms, but I have not tested it myself.
You're gonna to do it, or some other future
ideas?
Yeah.
I'm sure. I mean, we support academic projects wherever, if it's of interest for us. And as I say, at the moment, the agronomic research we are doing is on the combating nematode systems. But and we are producing a lot of biocarbon from demolition wood now for metallurgic industries and for using as a reducing agent rather than fossil coal. So we are quite widespread. But of course, if there are some good ideas, we are happy to support and provide biochar samples for any testing of such ideas.
And last one, coming back to agriculture, you said biochar is suitable for agriculture. And there was a question for previous presenter about advances with wood fibers compared to use of biochar. And Sampo answered, this is too expensive to use biochar.
Yeah, but
farming. What can you say on that?
I would say that it's not too expensive, it's too cheap to do fossil use. I mean, if you look at carbon dioxide removal, the voluntarily carbon market is solely run by biochar applications. So voluntarily, people pay to sequester carbon, and biochar is by far the method that has been delivered the carbon sequestration. So when, of course, it's cheaper to take the woody fibers directly to soil, and it will last, as he says, for maybe 20 years. Carbon biochar would last for maybe 100,000 years, a million years. So the question is rather what you are willing to do to take the carbon from the atmosphere out of circulation. We will come to a point where this is important enough so that the value of that sequestration is paid rightly. And at the moment, it is like 180 euros per ton of CO2 equivalents. And 1 ton of biochar would typically have up to 3 tons of CO2 equivalents of carbon storage. So, the carbon credit market for biochar could be 3 times 180 euros, which is equivalent to the price you pay for the char market. But I think another important issue is additional benefit, not only carbon sequestration, but also that it could have other positive effects. And as I alluded to that, for instance, if you like to do biochar from sewage sludge, you recover phosphorus, yes, but you could also provide a very good sorbent for PFAS pollutants, for instance. So we have seen that you could really bind PFAS in soil with biochar from sewage sludge to the extent that you could eliminate up to the leaching in soil up to 99% by just adding 1% of biochar. So this is a good way to repair historical harm of soil quality already by using biochar for this type of purposes.
Paul, thank you for your good arguments, thinking about next generations. And one more comment, thanks to all presenters for great input of climate change technologies. Paul, thank you very much. Thanks for other guys. And Sampo, if you can take this one question, maybe last one, what we farmers have done definitely wrong so far, and what is the first step to regenerate soil fertility? That was
It's a great question.
Somehow.
It's a great question. First of all, I need to say that the farmers, as a soil caretakers, have always been. They have been doing the farming techniques that have been like taught and consulted. So everybody's doing, obviously, if you think about decades back, they've been doing the things that they think worthwhile. And for a long time period, at least, let's say till the last 20 years or so, the farmer's main task has been to provide food and to do it efficiently. And lack of food and energy for mankind has been the issue that the farmers, the historical task has been for farmers. And during the Green Revolution, the farmers got great results, and we, as the humankind, we managed to overstep hunger and all these kind of issues not totally, but the situation is better than, let's say, in the beginning of the 19th century or 20th century. The issue is that pretty much most of the things that you do in the field actively with machinery somehow releases the carbon. Like when you're cultivating, when you're seeding, you're cultivating the soil, which eventually will the carbon will evaporate as a carbon dioxide, and that is the problem. It depends what you are farming, like with normal crops like wheat and so forth. It's approximately, let's say, 200 kilos per hectare on mineral soil that you actually lose in carbon every year. And if you have hard soils, peat soils, it might be much bigger. In Finland, we have lots of discussion where you may be losing 2,000 kilos of carbon per hectare per year from peat soil. So it's somehow related to soil type as well. And most of the farming is monoculture and have been monoculture for many decades. And that is the problem. We have our soils exposed many months of the year for erosion, etc., etc. That is also adding up, like the debit we have. For carbon.
Yeah. Thanks for your expertise and thanks for.
Yeah, I'm
answer.
sorry.
No, it's okay. It's cool. Now what we can go.
Yeah.
I think
if I say two things you can do, pay attention to the crop rotation and use cover crops.
Perfect.
Those are the easy ways.
Perfect example. Thank you. And now, with no further ado, it's time for interactive feedback survey. And this will be led by Selma Solhagen from Biogas Oslofjord. Selma, the floor is yours.
Thank you. We're a bit behind schedule, so I'll try to do this efficiently because I guess a lot of you are daydreaming about lunch right now. What we want you to do is go into menti.com. Do you see my screen?
Yes.
Yes. So you go to menti.com and then you plot in the number, the code that you see here. That should give you access into the Questback survey, and I'll walk you through some questions. And let me know if there is anyone who are having. Yeah, I can paste the passcode in the chat. Let me see. Or I'll give you a direct link here. And I'll just move on to the next one while people are logging in. So you should be able to log in still and then answer the first question, which is what group you represent. And I can also say that we are doing this survey because part of the BREC project, we are developing information material regarding technologies within the bioeconomy. And we want the information to be as relevant as possible. I see that 12 people are logged in, but we're 35 in the meeting. So I'll just wait a little bit before we move on. And see, we have a lot of researchers here today, which I kind of understood from the questions, a lot of technical questions. I am going to move on. If you haven't been able to log into the Menti, it will still be possible, even though I move on to the next question, which is building on today's webinar topics. What would you be interested in learning more about? And this is an open question, so you can write one word and be as specific or general as you want. You see, we have a lot of different topics that people want to learn more about. So it seems like today's webinar had interesting topics to build on. And now I will move on to showing you an example of an information pamphlet. And this is what we want to get some feedback on and how to develop further and what type of contents we should prioritize. So the example is regarding circular phosphorus practices. And then first there will be information about what phosphorus is and the importance of it. You don't need to read every single word as I walk you through this. There will also be some information about how the phosphorus cycle works. And then there will be a section regarding challenges, specific challenges, like for phosphorus, we have food security as an issue, and eutrophication, and inefficient linear use of the nutrient. I'll give you a little bit time to read. And then following a description of challenges, we will present different types of solutions. So an example of a solution that we have is druite extraction, and then explaining what it is and how it can help with solving some of the challenges presented. And listing the benefits in this case. So this was just an extraction of a draft regarding phosphorus. And then we have some questions regarding this. In regards to the info letter presented, can you rank these statements from strongly agree to strongly disagree? And then you can slide for each of the statements where you whether you agree or disagree with the statement. And then I think we move on to the next one, as 16 of you have answered already. And this is the last question. How would you rank the importance of the following type of information when comparing bio-based technologies? So we want you to rank it from 1st to 8th. If there is any topic you don't want to include, you don't have to include it. But we would prefer if you rank all of them based on how you would rate their importance. Okay, thank you. Then I'll stop sharing my screen, but I'll leave the question open. So if you're still thinking about it, you can answer it regardless of me sharing my screen. And that was all the questions we had. And thank you all for answering.
Thank you very much, Selma, for this survey. We are done, actually. And Inga, do you have to add something?
No, no more questions.
No more
Thank you,
questions.
everyone. It's for the presenters and for the listeners.
Absolutely. I would like to express as well, sincere appreciation to today's presenters. I hope we got valuable knowledge, and we all are invited to join for our third webinar, which will take place next Friday, 19th of April. Thank you very much, and have a wonderful day. Bye. Bye.
Bye.
Bye.
Thank you. Bye-bye.
Bye-bye.
Bye bye.